That'll be next week.
Next week and the next 2 or 3 weeks. Electrical power sources and storage, that from the perspective of batteries. So we're really sort of 2 groups. That would be better. Types isn't quite correct, but 2 groups of electrical storage devices. The first group allows us to create a bunch of components, put them all together, and we've got electricity. Packaged up, ready to go, ready to be used. These all, even with the Nikon version, all have some degree of internal resistance that's relatively high because of the chemical nature of things. The second storage device, we can build a component, but it doesn't have any electrical potential until we charge it or give it the electrical potential. That's called a capacitor. Now, the big advantage of a capacitor is it will take the electrical charge instantaneously. Again, at the speed of light, it will charge up as fast as we want it to. Okay, and it will charge up remarkably stably. So let's say I don't want to charge it up fast. I want to charge it up over a period of time. So I feed the current through a known quantifiable resistor until I get to some voltage threshold. Then that would be a way of measuring time, okay, depending on the size of this little capacitor. So it'll repeat itself very, very accurately. Whereas a battery, every time we charge it up and discharge it, it's going to change just a little bit.
So that's to prevent spikes, capacitor?
Well, there's a bunch of things we use them for. Always and for all kinds of different things. But at the end of the day, they're a big parking lot for electrons. Right? Just like a battery is. So the 2 big differences is the battery, if you put all the components together, it's good to go. It's got juice. It's got electricity. Capacitor, you have to charge it for it to have electricity. Also, the battery will retain its electricity for quite a long period of time. The capacitor, over a very short period of time, from milliseconds to maybe a minute or so, will self-discharge. So it's really, capacitor is meant to be instantaneous but temporary. All right, so I mentioned the term earlier, the galvanic relationship between 2 different metals. And again, it could be very similar metals or the same metals but different compounds of them. So for example, a very common battery is lead-acid battery. And the lead-acid battery is composed of lead and lead peroxide, which is almost lead. Pretty close to lead. Let's see. Dig this one out of here. So yeah, lead acid battery. We've got plates of lead, and then a little difficult to separate them, but you can see it's slightly different color. That's lead peroxide. See a slight redness to it. Now these are fully charged plates. The other set I've got in here are fully discharged plates. So ultimately, one of these will always be anodic, the other will be cathodic. So there'll be an anode and a cathode. And I'm not going to get into all of the different things, oxidization and reduction, etc. The flow of electrons, in the case of charge, we will pull a bunch of electrons out of the positive side and shove them down the negative side. Chemically, it's going to be going the opposite direction. The electrons in chemical reaction is going to be going the opposite direction here. In the state of discharge, we're going to allow all the electrons to come out of the negative side and back into the positive side. as we do this, the chemical reaction is going to happen internally. It's going to happen through what's called an electrolyte. There'll be some electrolyte that allows a chemical reaction to occur. The chemical reaction is essentially going to be corrosion. Okay, and typically it's the anode. I'm going to say this right. It's the anode that corrodes. The cathode changes state. And then when we go to charge it, we're going to reverse that condition, hopefully. Now, we'll never, ever reverse it exactly 100% perfectly. So each time we do this cycle, each time we do this dance, things are going to change just a little bit. The end result is, the other thing that needs to occur is in the chemical side of things, the individual plates cannot electrically conduct with each other. Okay? If that happens, the other plates will try to conduct in a closed loop inside the cell rather than going the other direction. Okay, so we have to keep these different, the anodes and the cathodes, all separated from each other so that the only electron transport occurs through a chemical reaction in the electrolyte. It's also important to note that in a battery, the electrolyte can be catalytic, meaning it causes the reaction but doesn't itself change, or it can be reactive where it also changes. It changes its state. Okay? So in a NiCad, the potassium solution in NiCads, it's a catalytic reaction. It doesn't change at all. And all your acid or lead acid batteries, the hydrosulfuric acid does in fact change chemically in a different compound.
What do you consider an electrolyte? Water?
What?
What is an electrolyte?
An electrolyte is anything that helps create an electrolytic reaction. So a chemical reaction based upon electron exchange.
So water, like you said?
Well, water is part of the solution, but in and of itself isn't part of the electrolyte.
Salt.
It's a sulfuric acid. So remember the orange I told you about?
Yeah.
The citric acid in the orange is what's creating the electrolytic reaction. There's also a bunch of water in there. That's part of the transport. That's what puts everything in solution. Okay, but and we can also have it dry. All your primary batteries, AA, AAA, the electrolyte is a solid, or it's a semi-solid.
It's a salt.
Salt can act as, some of the salts can. More often than not, what you need is either a fairly strong base, like in the NiCads, or fairly strong acid in the lead acids, or other heavy metal acids.
You need an anode, cathode, electrolyte, and then there's a fourth one for the chemical reaction in the battery, right? That's what he's talking about.
Because you lost me on that.
So
Of
for
the
the
components, you got to have an anode, a cathode, and the electrolyte.
Okay.
And then an outside circuit.
there we go. Yeah, that's what I'm getting at.
You got to have an outside circuit.
An outside circuit to complete the current flow.
Right.
Okay.
Otherwise, what's the point?
You have no current flow then.
Right. And it just sits there. It will eventually. All batteries will eventually auto discharge.
Okay.
So, and that means the chemical
Eventually
reaction is happening.
It will
Now-
decay.
A typical lead acid battery, they auto discharge pretty quickly. So I'll talk about that later. Okay, how many electrons will this unit store?
How many?
A lot. How much? An awful lot. Okay? A yoda of electrons. A yoda times a zeta of electrons. It really is going to depend on a number of things. Obviously, the amount of material that's in there. If I make a battery as big as this room, it's going to store more electrons than this little bitty one, right? So the chemical nature of the metals used to make the plate will have some variation in the amount of electrons, or the amount of electrons stored. But more so, the chemical nature of the metals will determine the voltage potential between the two metals. Okay? So I don't know if did they cover the galvanic chart in general when they were talking about corrosion?
Yeah.
So if you look at the galvanic chart, there's, I forget what the metals are, but there's a long list of them. And regardless of where you are in the chart, the further away you get, the more corrosive it is, right? Well, that's also true, the further apart you get, the more voltage potential exists between the two, okay? However, the other way of doing this is instead of saying, if I want more voltage, instead of getting two metals that are really, really far apart, what I could do is make a little bitty cell and then put it in series with another little bitty cell, in series with another little bitty cell, and just start stacking all the voltages together if I want higher voltage, okay? Which is what we've done here. 2.1 volts, 2.1 volts, 2.1 volts, 2.1 volts, 2.1, till I get up to something close to 12, actually 12.68, okay? Or 24, or whatever I'm aiming for. So chemical nature, obviously the electrolyte itself. Okay, is it orange juice? Is it hydrosulfuric acid? Depending on the metal, or if we went with the nickel cadmium arrangement, we used a base. Certainly the temperature of the material, and this is particularly true if the temperature is getting down to the point that whatever liquid we use to suspend the electrolyte in is starting to do things like solidify on us. Okay? But solidification doesn't necessarily mean it will stop working. One of the areas that we played with batteries, with the lead acid type batteries, is to actually gel the electrolyte. Okay, suspend it in a silica gel. It's still transport, it still works. Okay, but when it gets frozen solid, it doesn't work so well. More badly though, unfortunately with water, when it freezes, unlike all other material when it freezes, it shrinks quite a bit. Water says, all those little hydrogen and oxygen molecules line up. So it actually stretches a little bit. And anything in the way gets broken. The hydrostatic force from water freezing is extremely powerful. To shatter the case, break plates, crack trees, shatter milk bottles.
So do they have that problem like in Alaska or anything?
Anywhere. Now, one of the things we're going to do is we're going to dissolve a bunch of hydrosulfuric acid into the liquid, which is going to lower its freezing point quite a bit. But nonetheless, minus 57 degrees or whatever it gets in Alaska, really cold, beyond cold, okay, below cold. Yeah, it can happen. It can shatter a battery. So one of the things you can do is A, keep it charged, and B, keep it warm. So the amount of metal that's exposed, the amount of surface area is going to be really important. So if I take a big bar, an ingot of metal, it doesn't have a lot of surface area, right? So I take it, pound it out real thin so it's a nice big plate. Yeah, it's got a little bit more. But if I instead take it, shred it all up, and then compact it together so it's kind of like a sponge, now I've got a whole bunch of surface area. Okay? Now, of course, that sponge, as it forms and unforms and forms and unforms, it's going to tend to fall apart. So what I might do is I might take that sponge and press it into a little grid that sort of helps hold it together. But even there, you can see some degradation occurs, right? And little bits of it fall out. That's essentially what fails the battery. Eventually, enough of these will fall out, go down to the bottom of the battery, and may eventually even short the bottom of the cell. Okay, so we make it porous. Now, also recognize as well the ability of the electrolyte to circulate. Because remember, this chemical reaction is going to occur fairly close to the metal, the two different metals. And then stuff sort of has to circulate. It's kind of like heating up, okay? It's going to be real hot close to the heater, and until the air starts stirring up, you don't get the heat out into the living room. Okay, same thing is true here. That chemical reaction is going to occur quite a bit in and around the surface area of the metals, but that cell has to circulate. Well, as it heats up, and by the way, the chemical reaction is going to include some gassing as well. So sometimes the gas bubbles going up help stir. Other activity in there can help. But what you'll find is if you go to charge a battery and then come back, things will have stabilized. You charge it, then turn it off. Here's your voltage. You come back a day or 2 days later, and things will have dropped. Or conversely, the reverse is true. You discharge a battery and it's depleted, it's done. Well, what you've done is you've depleted everything in the immediate adjacent area next to the plates, but come back in a half an hour and hit the starter again, and you get one more wah 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 out of it. Okay, again, things got to circulate just a little bit. Now, it's also important to note that we have some, we tend to do things in the world of electrical in a manner of what we call preferred status. So the preferred value of voltage is 12 volts and 24 volts. And occasionally you see a 36 volt system out there, but it's pretty rare. Okay. The same thing in terms of preferred values are going to be usage. So we tend to say, for the most part, a battery is going to start an engine. Well, that's a high current draw over a fairly short period of time. However, there are a lot of applications where we use a battery. Now, when we do that, we start the engine and we charge it right back up. We don't deplete it very much. Okay. On the other hand, there are some cases where we want a fairly low amount of current over a long period of time. Okay, like in our motorhome or in our boat, running the lights and the toaster and whatever else. Okay, so that's a very different mission profile. So we might want that battery to sort of go through a long state of charge or discharge and then be recharged, or a deep cycle versus a high cold cranking amp shallow cycle. So we're going to design the battery quite a bit differently for different mission profiles, right? Okay, so that means some other characteristics are going to be how much current can it give in the short, immediate, boom, 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 versus how well does it do being very deeply discharged and then recharged and not fall apart, okay? So within the battery world, they use the term primary and secondary cells. Essentially, a primary cell is, it's a
Battery.
Well, there's a 9-volt battery. Okay, note it's actually 6 different cells, 6 little biscuit cells. Okay, these are all primary cells. There's actually another version of this in here. Yeah, this one's a little different. What they did is they made 9 little tall, or 6 little tall cells. Each one of these are 1.5 volts. That gets you 9 volts, right? Okay, because it's really hard to make 9 volts out of a simple little primary battery. The idea behind these guys is you use them, throw them away. Don't throw them away, recycle them, blah, blah, blah. Okay, that was my environmental consciousness statement. Yeah, but bing. The truth is you can recharge them, but they don't work that well. And you can get them really hot, and that's not so good. But I played with it, and it's like the first time you recharge it, I got like 10% out of it. It wasn't much.
Yeah.
Second time, it was nothing. So they really are a one-shot deal. There's the anode in this case is the outer case. Cathode, the graphite rod is in the middle. Here it looks like a paste of nickel metal chloride or nickel hydrogen chloride. And they don't tell us what that one is. Oh yeah, they do. Internal zinc, and then a brass stud for the positive. That's interesting. So in that case, the zinc is your anode, and the brass would be your cathode.
Which direction is the current going through on those batteries?
So it's coming out of the negative
Okay.
and going to the positive for discharge. Now, if it's a secondary cell where I can charge it, when I'm charging it, it's going to go the other way. We're going to pull them out of the positive and shove them back into the negative, just like filling the tank.
Okay.
So here's an example of various different battery states. But the point of this particular note is really sort of talking about how much surface area, how much porosity. The more porosity I have, the weaker the structure is going to be. So as it discharges, you can see it start to change shape and state. And eventually, if it gets really crystalline, parts break off, and the parts that break off are no longer in the electrical circuit, so they don't reform. Okay? Now, there are some ways to rejuvenate lead acid batteries a little bit, but one of them is you pulse them with a high shot of current rapidly. So the predominant thing based upon voltage is the galvanic relationship of the two metals and the electrolyte being used, as well as the internal resistance. So a lead acid battery tends to have, as batteries go, a relatively high resistance. The other end of the spectrum, one of the lowest resistance batteries out there is a NiCad. So one of the reasons why you do not ever want to use a NiCad battery on any other kind of charger or a NiCad battery charger on any other kind of battery, because they're expecting very, very different resistances. And if you mismatch, one or the other is going to give you way more current than you expected. The upside of the NiCad battery is there's some instances where you need a whole lot of current, like starting a turbine engine. That's where we use them a lot in aviation. Well, we finally got pretty good at making lead acid batteries that can do that. And frankly, NiCads are a total pain in the butt to maintain. So as far as I know, they're not being used in aviation anymore. There may be some out there. They're really high maintenance.
Is the new battery gonna still, without this having all the cycles, still gonna corrode and fall apart like that?
New battery will self-discharge.
Okay.
So, and if you just don't do anything with it, in fact, the worst thing you can do to a new battery is not use it.
Right.
That's one of the problems we have here. I take a new battery, throw it in service, and start it, 2 or 3 times a month or more. Typically, I'll get anywhere from 5 to 8 years of life out of it.
Yeah.
These where we don't use them that much, I'm hard pressed to get 3 years of life out of them. We just don't use them.
Are battery tenders good for them if they're being always constantly charged?
Well, you don't want to constantly charge them.
No.
You want to sort of keep them at the same level. So a good quality, high-end battery tender, yes, because it does that. Okay, $39, or $12 fries special. Okay. Again, I'm not going to test it too heavily on this, but in a lead acid battery, we use porous lead for the anode and lead peroxide for the cathode. We'll use a little bit of H2SO4, hydrosulfuric acid, mixed or diluted with water. Hydrosulfuric acid is pretty nasty stuff. I actually used to work in a marine lab where they used pure hydrosulfuric acid. It was at like 99%. And it came in this big, weird material. It was a form of ceramic material in a jar like this, double sealed, and that was suspended inside this big, huge Nalgene plastic container. Because there was nothing. If that got out of that bottle and got onto any surface, it would just eat right through it.
Except plastic though, right?
Huh?
Does
The
it?
plastic was physical protection. It would eat
Right.
through the plastic.
It will?
That was just physical protection from something hitting it. But the ceramic material that they had it in, and that was in a dry form. But even, the problem was in a dry form, as soon as you pull it in the atmosphere, there's enough moisture to where it's going. Yep. It's nasty stuff. In this case, and I forget, it's like 35% or 37% solution. So yeah, that's showing the grid framework as well as sort of the porous active material. That's sort of showing the two there. Now, the other important thing to note is, if I take a bunch of water and I add a little bit of caffeine, a little bit of brown, some carbon dioxide, and 27 grams of sugar, put a red label on it, I call it Coca-Cola. Okay? Now, if I take that 12 ounces of Coca-Cola and throw the 27 grams of sugar in it, that volume of water is going to get bigger, right?
I hope so.
No, actually it's not.
No.
No. What's going to happen is the sugar is going to dissolve into the water. Now remember, water is liquid, and it's got all these molecules that are all sort of laying on top of each other. As the sugar dissolves, it's going to start filling in some of those gaps at a molecular level. So what's going to happen is, I'm still going to have 12 ounces of liquid, and I'm going to throw all that sugar in there, and my volume is going to have expanded a very small amount. I might have to heat things up to get this to work, but my volume is going to have expanded just a very little amount. But the weight of what I've got is going to be quite a bit more. So I have 27 additional grams. Okay, still 12 ounces of liquid. Now I take my Diet Coke, which has got like a microgram of some sweetener in there. Okay, same 12 ounces of liquid. Both of them have a little carbon dioxide in there, so there's a little bubble in there. Now if I take a bucket of water, go home, try this in your sink, fill your sink up. Take the diet soda, set it in there. Take the regular soda and set it in there. The diet soda will sink down and then eventually come back up and float just under the surface. Because there's enough air in there, enough gas in there to float the aluminum. The sugar soda is going to go boom, down to the bottom because it weighs 27 grams more. The density of the fluid in the diet soda is going to be quite a bit less. The density in the sugar soda is going to be quite a bit more. We do this in salt. How many of you guys ever been swimming in the ocean? And then gone swimming in a pool where it's fresh water? Okay? In a pool, I sink to the bottom. I cannot swim, I sink to the bottom. I was a commercial diver for years, and it was really good in salt water. Even in salt water, I sink to the bottom. In a pool, I'm done. Now you go out to the Salton Sea or the Dead Sea where there's a whole lot of salt in the water. I dive in there, you know what happens? It spits me back out. Literally, I go clunk, boom, and blob on the top. Because the density of the water with all that salt in there makes it way more dense than I am. Okay? So, based on Archimedes' principle, my body, the salinity in my body, and even the bones and everything else, is less dense than super salty water. Same thing with the two sodas. The density of that sugar soda is so much higher. It turns out that Archimedes said, if you can get it dissolved in there, and a chemical reaction doesn't occur, that's bad. Chemical reaction makes all bets off. Then what's going to matter with respect to buoyancy is the average overall density. Okay? So compared to water, what's the average overall density of an aircraft carrier? More or less?
Less.
Gotta be, or the aircraft carrier would be a submarine.
Right.
Right? But all the air inside there is part of that average. All the steel and the jets and the fuel and the whatever else, the wiring. Boy, they got a lot of stuff in an aircraft carrier. But all that stuff, the average density of it is less than the average density of the water. Okay? If I throw a bunch of salt in the water, what's going to happen to the aircraft carrier?
It's gonna rise.
It's going to float up a little bit higher,
Yeah.
right? So I could use the buoyancy of the aircraft carrier as a way of measuring how much salt is in the water. Okay? Same thing is true here. The more of that dry hydrospheric acid that I dissolve into the water, the more my aircraft carrier is going to float. Now it's going to dissolve really fast. So I'm going to have to make my aircraft carrier out of something that doesn't dissolve in acid, maybe glass. Okay? In fact, I'm going to make my aircraft carrier really short and kind of tall. But nonetheless, it's going to be a little boat that floats inside some of this electrolyte. And then depending on how much it floats, will tell me how much acid is in the mix. Now, the other thing that's important to note is as this discharges, the acid converts into other chemicals, and the electrolyte becomes more and more pure water. Okay, so it gets less and less dense. So the way to measure the state of discharge in a lead acid battery is to measure the density of the material with a little thing called a hydrometer. Now we can't do this with any other kind of battery. This kind of battery lets us do that. Okay, so the lead becomes lead sulfate on one side. If it loses a couple of hydrogen in the form of gas, sends a few electrons around the circuit, the lead peroxide also becomes lead sulfate. If it gets the 2 electrons from the circuit, as well as potentially some of the hydrogen, and The electrolyte obviously gives up some of the hydrosulfuric acid, but does gain a couple of water molecules out of this chemical reaction. And again, I'm not going to ever test you on that. Just know there's this chemical reaction happening, and the solution becomes less and less sulfuric acid and more water. So it becomes less and less dense. Now, as it becomes less dense, it also makes it easier for it to freeze at 32 degrees. So having a discharged battery in cold weather isn't a good thing.
And we're adding distilled water for what reason?
Well, we don't care that it's distilled, we care that it has contaminants.
To
Does not have
suspend the-
contaminants.
Yeah, it's not getting rid of the contaminants.
Okay.
Deionized, we don't care, we just don't want the contaminants, we want pure water.
Yeah.
Contaminants are usually base minerals, so they neutralize the acid anyway.
Got it. Okay.
Does that change the density as well, correct?
Well, it just neutralizes it, and it
Okay.
just, they,
They neutralize it.
the
back
two
to water?
interact and they do nothing, yeah.
Okay.
Okay, so the lead changes, the water changes, everything gets weaker. At some point, if you take it too far, you'll never be able to get it to come back. Okay? Now, throughout all of this, you're gonna have some voltages. And the voltages are gonna decline a little bit, and then start declining faster and faster and faster. Depending on the battery type, the way that curve looks is a little bit different. NiCad battery tends to stay right at top voltage for a long time. And then at about 95%, it goes boom and tanks. Okay? Lead acid, on the other hand, sort of stays good, and then about halfway starts dipping down, and then at about 2/3 it starts tanking faster and faster. Okay? Okay. So yeah, in fact, I took pictures of this apart, because quit taking it apart. So you can see the lead peroxide, and you can even see just sitting on the shelf some damage occurred. Here is your lead sulfate from the porous lead and lead sulfate formed from the lead peroxide. They look a little different because of the direction they're coming from. But if I continue to do that, what you would get is both of them looking closer and closer alike.
They're trying to become one, right? Is that what it is?
Well, they're not trying to meld into each other, but they're both heading towards pure lead sulfate. Yeah.
And what was the brown layer between?
That's the lead. That's just a separator.
a separator.
That's just a separator plate that sits in there. It's whatever it is. It can be. It's usually not an organic paper, but it's a type of material that will not dissolve in the sulfuric acid.
Not dissolved.
Right.
Okay.
And is also not electrically conductive.
Okay.
Both of those ingredients required.
So it's like it's an inert piece of paper. Is that what you're saying? Like it's
Well, direct paper itself would dissolve in the sulfuric acid. Organic compounds would. So I'm not quite sure what it's. Some kind of a polymer material. I'm not sure what it's made out of. But so, anyways, what we've got is, instead of the Pacific Ocean or the Atlantic Ocean, we've got the little bitty tall ocean. And inside it, we've got the shortest aircraft carrier in the world, but it's got a nice mast on it, right? Okay. And we're going to take and maybe put a few little BBs in there and get the thing sort of straightened out. And what we're going to do is we're going to say, if everything is really dense like the Salton Sea, this little boat's going to float real high. If it's really not very dense, it's going to sink way down. And then we're going to create a scale. We don't care what the scale is. Just like we could say there's 12 hours on a clock or 24 hours on a clock. We don't really care. But what we do want to do is reference it to something, some common denominator. So for specific gravity readings for all gases, we compare it to the base gas, one atom, or one electron, one proton, no neutron, hydrogen. That's the baseline for the specific gravity of all gases. The baseline for specific gravity of all liquids is pure H2O. So we call that 1. Anything denser than 1 is going to be a number higher, like 1.2, 1.275, 1.3. metal is like 27.9, whatever that is, it's just a rating scale as compared to pure water. Okay? So the specific gravity, which is really sort of telling you overall density of the material, in this case, as I start pouring lead acid or acid in there, or sugar or salt, okay, if I took the specific gravity of the diet soda, this guy wouldn't float very well. If I took the specific gravity of the 27-gram sugar soda, it would float very well, right? Well, same thing is true here. However, what we're going to do is we're going to just put a fancy little scale on here, and we'll give you a number. Instead of saying 1.1, 1.2, we'll just say 1100, 1110, 1112, 11, because only maintenance people are going to be using this. This is tailored specific to our industry. Okay, a scientific one will look very different. Actually, for electronic now, I've got one. But so ultimately, and also note there's sort of a red and a yellow and a green. Sort of bad, sort of good, sort of really good. Okay. The truth is, you guys are gonna go through this entire. I want you to measure every cell, measure the voltage, put it back on the charger. Every cell, measure the voltage, put it back on the charger. In truth, with the hydrometer, for the batteries you can actually get into, which is only going to be one type of aviation batteries, they've eliminated the ability to get into batteries in the automotive industry. Most of the motorcycle industry as well. They've all gone to fully sealed absorbent gas mat type batteries. So what we're really trying to verify in a practical sense is the battery charged? I'm in the green, it's probably charged. Check each cell. I'm sort of in the middle down here, throw it on the charger for 12 hours, come back. Did it charge? It's not charging, battery's a problem. Okay? You're really sort of doing a bit of a go, no go. All you're really trying to say is, I've got a complaint. Usually the complaint is, things stop working. Doesn't start. Okay, you don't know if the battery's bad, the generator's bad, the starter's bad. But if you get in there and the battery has no juice, that's where you got to start, because without juice, you can't test anything else. Okay? So you pull the battery out. Check the specific gravity. Oh, yeah, it's all low. And in fact, I open them, there's a bunch of guns, yucky in there. From the get-go, you're going to then say, that cell might be bad. That cell might be shorted. I don't think any of the ones that we have here are shorted. One of them might be. But so at the end of the day, I want you to do a little bit of scientific precision for the work we're doing. Try to get some good numbers, some good data. It gives you a chance to collect data and get practice at it. But in the real world, you're really trying to say fairly quickly, is this thing charged or discharged? If it's discharged, charge it. If it's already charged, use it to get the rest of the system working and tested. Okay? All right, so the hydrometer. Now, what happens if I get real cold here? Does that affect density?
Yeah.
Is that going to affect how low my aircraft carrier floats?
Yeah.
Yeah. So we might have to do some calibration and
Colder the water will be
correction.
more dense, right?
So we might have to do some calibration and correction for that.
Correct the temperature,
Are there FAA test questions around that?
most likely.
Yeah. So read in your book. I'm strongly tell you, read in your book about what you're going to do. If it's colder, how much do you correct? Most of the time, what they do is they say if it's 80 degrees outside, there's no correction either way. I happen to have a hydrometer where they pick 70 somewhere in my hangar, where 70 was zero. Doesn't really matter. You pick a 0 point and then subtract one way, add the other way. The truth of the matter is it's all stupid. It really is. Who cares? All I'm trying to say is, does the battery need charging or discharging? So what? It's off by 12 points on a scale of 1,300. Right? You know, I mean, so it's right on the line of red and yellow instead of into the red a little bit. Either way, it's getting charged.
Still needs charge.
Yeah, right?
Are you saying a battery can be overcharged as well?
What overcharge looked like is you can't get any more hydrospheric acid out of the plates.
Okay.
So you can't overcharge it there. What happens once it's fully charged is it continues heating and continues producing gas. So it starts morphing the water into a gaseous state.
Right. Yeah. Now
That's why it gives off hydrogen and they blow up.
Well, there's really two
Or they
potentials
get
going on when the blow up. One blow up is a combustion hydrogen lighting. The other is the pressure vent doesn't work out, pressurizes and blows up. Hard to say which
So
causes
as it
it.
outgasses, the pressure's gonna increase if it can't relieve it.
Right. So basically, yeah, it is 37%. The rest is pure water. That's going to get us about 1275 to 1300 on the hydrometer reading
For the density.
for the density. Correct. With pure water being 1.000. Okay. Voltage of any cell in a stabilized state can not be any higher than 2.113. Now, if I hit it with a 40 amp charger, a couple hours, pull it off and measure the voltage of each cell, they're all probably going to be close to 3 volts because I've super zapped it. But if I shake it up a little bit, set it down, come back in about 4 or 5 hours, they'll all have settled out to about maximum 2.113, which if you multiply that times 6 gets you to 12.68 volts. So your charging system, to be able to charge this, has to be able to produce more than 12.68 volts. Or it's not charging, right? Okay, if the
Yeah.
charging system is less than this is going to be supplying the voltage.
Yes.
So the very first denominator, once you get this charged, is start everything up and measure the voltage at the battery. If the parallel voltage is higher than 12.68 volts, then you know the charging system is doing something. Now what it should be, it depends on the battery type. For a typical lead acid battery, they like to be at 12.68 volts. Other battery types like to be a little bit higher. So you're going to want to see about a volt higher, 13.68 to 14 volts. With the AGMs and some of the newer batteries, which they'll talk about next week, you actually want to be about 14.2, 14.5. You also don't want to mix technology. I put that 14.5 volt charging system. If I put a regular lead acid in there, it isn't going to last very long. It's going to overheat it. Oh yeah, so this shows the scale here. And note they lost the decimal point. It just, I'd be still throw it on the charger. Here, if I was in a hurry, maybe not. Down here, no problem. Go on to the next test. Right? Check the charging system, check the starter, check the whatever it is you're doing. All right? Okay. I think that's where I want to go. I know that's where you guys want to go. Yeah. All right, so yeah, let's quit here.
Quick question on the battery. The lead peroxide was the anode or the cathode?
I think the lead peroxide is the cathode.
Yes,
Look it up.
you're right.
I think it is.
You're right.
I never try to remember that stuff too much because I don't care. I'm never going to go into the battery to find out.
Right.
So,
It's